In this lecture video, we'll be estimating population means when the population standard deviation is not known. When we're estimating a population mean, our best point estimate is a sample mean. So we'll center our confidence interval on that sample mean, and the width of this range of values is determined by the margin of error. And once we have our confidence interval, this is the range of values that we feel confident contains the actual population mean. When the population standard deviation is not known, we must use the sample standard deviation in calculating our margin of error. We must also use the student t distribution instead of the z distribution. That means our critical value is t sub alpha over 2. We can also use our calculators to construct these confidence intervals. The calculator function that we will need here is t-interval. Let's review the notation that we're going to need for this process. Mu is the population mean, while x bar is the sample mean. Capital E is the margin of error, while lowercase n is the size of the sample. Lowercase s is the sample standard deviation, and df stands for degrees of freedom, and it's equal to 1 less than the size of the sample. Degrees of freedom is the number of data values in the set that have freedom. For example, suppose we have 10 data values and the mean of those values is 90. Then it must be that the sum of those 10 data values is 900, so that when we divide by 10, we get 90 for the mean. The first 9 data values can be whatever they want, but that 10th value must be the right number so that the sum of the 10 numbers is exactly 900. In other words, we have degrees of freedom equal to n minus 1, or in this case, 9. It's the number of data values that do have some freedom. When we're calculating our confidence intervals, it is important that we round correctly. If we're given the original set of data, we need to round our confidence interval limits to one more decimal place than what is used for the original set of data. If we are instead given summary statistics, then we'll go ahead and round the confidence interval limits to the same number of decimal places that are given with the sample mean. As we get started, let's make sure that we know how to find our t sub alpha over 2 values. We'll do 2 examples of that here. The t distribution does depend on the number of degrees of freedom. That means we'll have different t sub alpha over 2 values depending on both the confidence level and the degrees of freedom. In this first example, we have a confidence level of 90% or 0.90. That leaves 10% or 0.10 left over for alpha, and alpha over 2 then is 0.05 or 5%. We are also given that the degrees of freedom is equal to 5. We'll put our confidence level 0.90 in the center of our distribution, and note that our alpha over 2 value of 0.05 is left in each tail. T sum alpha over 2 is the value that separates the alpha over 2 portion in the right tail from the rest of the distribution. Some details that are included on the t distribution table are the area in one tail and the area in 2 tails. Notice that the area in 2 tails is equal to alpha, and the area in one tail is our alpha over 2. Let's take a look at the t distribution table. Degrees of freedom is down the first column, and in our example, we have degrees of freedom equal to 5. Our area in one tail is equal to 0.05. Equivalently, the area in 2 tails was 0.1. Finding where these meet up in the body of the table, we find our t sub alpha over 2 value to be 2.015. For our second example, we have a confidence level of 95% or 0.95. This leaves 5% left over for alpha, and cutting that in half, we have 0.025 for alpha over 2. We are also given that our degrees of freedom is equal to 122. With 0.95 in the center of our distribution, we have just 0.025 for our portion of alpha over 2 in the right tail. And t sub alpha over 2 is the value that separates that right tail from the rest of the distribution. Let's again take a look at our t distribution table to find t sub alpha over 2. This time our degrees of freedom is 122. If you scroll down to the bottom of the distribution table, you'll notice that we have options of 100 and 200, but not 122. In the case that the degrees of freedom lands between 2 values on the table, choose the one that's closest. And if it's too close to call, that is, the value's right between the two, round down to be more on the conservative side. So in this case, with degrees of freedom equal to 122, on our table, we'll use degrees of freedom 100. We have an area of 0.025 in the one tail or 0.05 in two tails. So using the value in the middle column that's associated with degrees of freedom 100, we find our t sub alpha over 2 is 1.984. Similar to the INV norm function in your calculator, there is an INVT function. In the DISTR menu, option 4 is INVT. You'll need to put in the left area associated with the t sub alpha over 2 value. In our first example, the left area was 0.95 and our degrees of freedom was 5. Rounding to 3 decimal places, we get the exact same t sub alpha over 2 value that we found on our table. For our second example, we have a left area of 0.975 and degrees of freedom 122. Notice at this time, the degrees of freedom that we are entering is different than the degrees of freedom that we use in the table. To 3 decimal places, we do get a slightly different answer, but using both our calculator and the t-table, our t sub alpha over 2 values agree to 2 decimal places, 1.98. Now that we know how to find our t sub alpha over 2 values, we are ready for an example. In this example, we are told that a random sample of the birth weights of 186 babies has a mean of 3,103 grams and a standard deviation of 696 grams. It's also noted that these babies were born to mothers that did not use cocaine during their pregnancies. The best point estimate of the mean weight of babies born to mothers who did not use cocaine during their pregnancies is going to be this sample mean of 3,103 grams. And we'll construct a 95% confidence interval estimate for the mean birth weight. We have a sample size of 186, which gives us a degrees of freedom of 186 minus 1, or 185. Our sample mean is 3,103, and our sample standard deviation is equal to 696. The confidence level that we are interested in is 95%, or 0.95. That leaves 0.05 left over for alpha, and cutting that in half, we have that alpha over 2 is equal to 0.025. We'll first construct this confidence interval by hand, and then I'll show you how to construct it using your calculator. We have our confidence level of 0.95 with alpha over 2, or the area left in one tail, of 0.025. That means that our t sub alpha over 2 value has a left area of 0.975. Looking at our t-table, the closest degrees of freedom value to 185 is 200. And our area in one tail, our alpha over 2, is 0.025. So we find our t sub alpha over 2 value of 1.972. If you use the INVT function in your calculator, you will be able to put in a degrees of freedom of 185 exactly, rather than rounding to 200. This will give you a t sub alpha over 2 value of 1.973. So our two values do agree to 2 decimal places and are just barely off in that third decimal place. This has everything to do with using a degrees of freedom of 200 versus a degrees of freedom of 185. But both of these methods will give you enough accuracy for constructing your confidence interval. To calculate our margin of error, we need t sub alpha over 2 times the sample standard deviation divided by the square root of the sample size. So we have 1.972 times 696 divided by the square root of 186. Rounding to no decimal places, since that's what was given as our sample mean, we find our margin of error to be 101. And constructing our confidence interval, we have x bar plus or minus e. That's our sample mean, 3,103, plus or minus our margin of error, 101. This gives us an interval from 3,002 to 3,204. Now I'll show you how to construct this interval using your calculator. Heading to the Stat menu and toggling over to Tests, we want option 8, t-interval. Since we have summary statistics, we want to choose Stats, and we'll enter our sample mean, 3,103, our sample standard deviation, 696, our sample size, 186, and our confidence level of 0.95. Pressing Enter while Calculate is highlighted gives us the same exact interval that we just calculated by hand. Rounding to no decimal places, we have 3,002 to 3,204. The moral of the story here is that whether you calculate all of this by hand and use your t-table or go directly to your calculator, you will get the same confidence interval. It is important that no matter which method you use, you know what the answer means. In this situation, we might write something like, we are 95% confident that the interval from 3002 to 3204 contains the actual population mean weight for babies born to mothers that did not use cocaine during their pregnancy. Now let's compare the results that we just found to this confidence interval that's obtained from birth weights of babies born to mothers that did use cocaine during their pregnancy. The interval is 2,608 to 2,792. The question is, does cocaine appear to affect the birth weight of a baby? Let's draw a number line to help us compare these two intervals. The interval that we calculated in Part B was 3002 to 3204, and we can approximate that on our number line by marking from about 3000 to 3200. The second interval given here is from 2,608 to 2,792, and we can mark that on our number line by shading from approximately 2,600 to approximately 2,800. Looking at these two confidence intervals, they have nothing in common. There is no overlap, and there's a considerable gap in between them. That does suggest that these two populations do in fact have different population means. That concludes this lecture video where we learned how to construct a confidence interval to estimate a population mean when the population standard deviation is not known.